And now the moment we've been waiting for, or not, triple integrals in spherical coordinates. So as a quick reminder, recall spherical coordinates are defined as from this figure here, and I've put them in your notes as a reminder. X equals rho sine phi cos theta, y equals rho sine phi sine theta, and z is rho cosine phi. Remember that x squared plus y squared plus z squared is equal to rho squared, and phi is between 0 and pi. All right, now let's let the function f of rho theta phi be continuous in a spherical box B, defined, so rho is going to be between A and B, theta is going to be between alpha and beta, and phi is going to be between gamma and psi. As usual, we're going to divide each interval into L, M, and N subdivisions. So that delta rho is going to be the quantity B minus A divided by L. Delta theta is the quantity beta minus alpha divided by M. And delta phi is the quantity psi minus gamma divided by N. Then for each box B sub I, J, K thus formed, we're going to choose a point, think Riemann sum, as shown in figure 5.57 of the textbook, reproduced below. Then we're going to define the integral in spherical coordinates as the limit as the number of intervals L, M, and N goes to infinity. Recall that that means that our delta rho, delta theta, delta phi are getting infinitesimally small of this quantity here. Because delta v is going to be rho squared sine phi, delta rho, delta phi, delta theta, as we can see from the drawing. Provided this limit exists, and then this can be written as the triple integral over our box of f of rho theta psi times rho squared sine phi d rho d theta d psi, or phi. Either way we could do it. Let's kind of go with the traditional. Let me change that. That should be phi. Not really sure how that became a psi, but oops. Yeah, yep, I had phi there. So let's try that again. It can be written as triple integral of f of rho theta phi, rho squared sine of phi, d rho d theta d phi. In case you've noticed, sometimes I'll say phi, sometimes I'll say phi. I've heard it pronounced both ways. So Fubini's theorem in spherical coordinates says that if f of rho theta phi is continuous on a rectangular box, where here we're saying in spherical coordinates, AB by alpha beta by gamma psi, then our triple integral is going to be defined as follows. The integral of f of rho theta phi, rho squared sine phi, d rho d theta d phi is going to be equal to the integral from gamma to psi, the integral from alpha to beta, the integral from A to B of f of rho theta phi, rho squared sine phi, d rho d theta d phi. As usual, we can always change the order of integration. You know the drill on that by now. To, for example, we can do d phi, d rho, d theta, or we can do d theta, d rho, d phi, et cetera, et cetera. Okay, so given a general solid region now, E equals rho theta psi, where rho theta is in the region D, and I don't know, man. Here, I'm having some technical difficulties, sorry. Let's try that again. E is the region rho theta phi, where rho and theta are in the region D, and phi is between two functions of rho and theta in R3. And of course, D is again the projection of our solid E onto the rho theta plane this time. And so we're going to have that the triple integral over our region of f of rho theta phi, rho squared sine phi d rho d theta d phi is going to be equal to the integral from alpha to beta, the integral from, let's say, g1 of theta to g2 of theta. No, that's not right. Sorry. I'm jumping ahead. Let's try that again. What we really have is the double integral over the region D of the integral between those two functions, right? The limits of phi of f of rho theta phi, rho squared sine phi, d rho d theta d phi. Okay, and if our region D is written so R is between two functions of theta, and theta is between alpha and beta, then we're going to have that my triple integral of my function, right, dv, so rho squared sine phi, d rho d theta dv, d phi. Sorry about that. That integral is going to be equal to the integral from alpha to beta, the integral g1 of theta to g2 of theta, times the integral from u sub 1 of rho theta to u sub 2 of rho theta, not times, sorry. So we're doing that triple integral of our function f of rho theta phi dv, which in this case is rho squared sine phi d something. Let's see, what's my order now? It's going to be d phi, d rho, d theta, which is actually, pardon me, we're going to pause a moment and correct the integral up above. Really not sure how I made that error. If you were thinking to yourself as I was writing, what is she saying? What is she writing? Let's just take that all over again. So hopefully you can see by what I've written this time that I really should have had f of rho theta phi up above, rho squared sine phi. Because phi is a function, is written in terms of functions of rho and theta, I have to integrate d phi first and then d rho, d theta, or d theta d rho, depending on which way things are defined. Okay, let's do an example and see how that goes. Let's evaluate the triple integral of 16z dv, where E is given to be the upper half of the sphere, x squared plus y squared plus z squared equals 1. So step one, of course, is to, get our limits of integration. So since we have the upper half of the sphere, first of all, the left-hand side just says rho squared. So we have rho squared equals 1. And we're in the inside of that. And so our rho is going to be between 0 and 1. Our theta, since it's the whole sphere, and when we do the projection down, we get the entire circle, theta is going to be between 0 and 2 pi. And since we're only in the upper half plane, phi is going to be between 0 and pi over 2. Right, when phi is 0, we're at the z-axis, and when phi is pi over 2, we are at, we're on the xy plane. Okay, so here goes. Now our integral becomes the integral from 0 to pi over 2, the integral from 0 to 2 pi, the integral from 0 to 1, 16 rho cosine phi, times rho squared sine of phi. I've chosen to integrate in the order, d rho is first. On the inside, so d rho, d theta, d phi. Again, that's of course not the only choice. Okay, let's rewrite the inside first into simpler terms. So that's going to give me 16 rho cubed. Now, however you'd like to do this, we can write this as sine phi cosine phi, d rho, d theta, d phi. Just for later reference, if you'll recall, we can write sine phi cosine phi as 1/2 sine of 2 phi. So this gives me 8 rho squared sine of 2 phi, d rho, d theta, d phi. Sometimes these little tricks, and they're not really tricks, but these little, uses of identities can save you some work in the long run. Okay, let us begin our integration. By the way, copying from one line to the next is an extremely, extremely important skill, and I hope that everyone develop it better than I apparently just did. We now pause for technical difficulties. Okay, so let's integrate with respect to rho first. So I'm going to have the integral from 0 to pi over 2, integral from 0 to 2 pi. That is going to give me a 2 rho to the 4th sine of 2 phi. Of course, evaluating at our limits. So we end up with the integral from 0 to pi over 2, the integral from 0 to 2 pi of 2 sine of 2 phi d theta d phi. Integrating with respect to theta, phi is a constant, so I'm just going to get 2 theta sine of 2 phi, and then of course evaluating at the limits, d phi, which is going to give us the integral from 0 to 2 pi. That will be 4 pi sine of 2 phi d phi. And computing the integral, that's computing the integral, I am going to get a negative 2 pi cosine 2 phi, that's my antiderivative, and I'm going to evaluate it at the limits. So I really have something against that pi over 2 clearly, since I can't seem to copy it right from one line to the next. When I plug in the limits, I get negative 2 pi. So you want to be careful here, right? That's going to give me cosine pi minus negative 2 pi cosine of 0. So that's 2 pi minus a negative 2 pi, which is also known as 4 pi. So just wanted to point out that you want to be careful there. Okay, let's see if we can look at one more quick example. So we're going to evaluate the integral, this time over a region E of xz dv, where E is the region above the sphere, x squared plus y squared plus z squared equals 4, and inside the cone that's pointing up and down, so it's in the z-axis, it makes an angle of pi over 3 with the negative z-axis and has x being less than or equal to 0. Okay, we don't actually need the equation of the cone unless you're dying to derive it, because we have all the information to obtain the limits. All right, so since the cone makes an angle of pi over 3 with the negative z-axis here, right? But our angle phi is from the positive z-axis. So what's the starting angle? The starting angle with the positive z-axis is going to be phi is equal to pi minus pi over 3, also known as 2 pi over 3. The finishing angle, well, that's going to be on the negative z-axis, right? Because that's where the other end is. So that's going to be pi. Okay, so that's phi. Now what about for theta? right? Since we know that x is less than or equal to 0, that tells us that if I'm looking in the xy plane, I'm looking on the left side, left half plane, in the left half plane, not the entire left half plane. So my theta is going to go between pi over 2 and 3 pi over 2. And finally, since E is bounded below by the sphere, rho squared equals 4, we know that rho is between 0 and 2. I do have another example, but that's actually a longer one, so I'm going to stop the recording once we finish this one. So our triple integral, dv, is going to be the integral from 2 pi over 3 to pi, the integral from pi over 2 to 3 pi over 2, the integral from 0 to 2, let's see, rho sine phi cosine theta, rho cosine phi, rho squared sine phi, d rho, d theta, d phi, which is the integral from 2 pi over 3 to pi, integral pi over 2 to pi. Let's just simplify what we have on the interior. We have rho to the 4th, sine squared phi, cosine theta, d rho, d theta, d phi. So we're going to integrate with respect to rho first, in which case, right, phi and theta are constant. So we're going to get 1/5 rho to the 5th, sine squared phi, cosine theta, evaluate at our limits. Without doing all of the algebra, I will just sort of jump to the answer, if you don't mind too much. Man, I gotta work on that copying skills, sorry. So I think I've got everything right now. So that's gonna give me 32/5 sine squared phi, cosine theta, d phi. And so now we're gonna integrate with respect to theta. When I integrate with respect to theta, phi is a constant, so I'm going to get negative 64/5 sine squared phi, cosine phi. What? Sorry, that's positive 64/5. No, that's not. I am totally writing that wrong. My mistake. Sorry, that's just a positive 32/5 sine of theta, and I'm going to evaluate at my limits and then integrate finally with respect to phi. So that's going to give me the integral from 2 pi over 3 to pi of, and when I plug in my limits, I get negative 64/5 sine squared phi, cosine phi, d phi. You can use a u-substitution, let u be sine squared phi, and if you do that, at the end of the day, you're going to end up with negative 64/15 sine cubed of phi, evaluated at the limits, and that is going to give me sine 64/15, the square root of 3 over 2 cubed, which when simplified gives me 8/5 root 3. I apologize that this video is a longie, and I'm going to stop recording now. So have a great day, and wait till you look at the next video.